Greetings, everyone. We're going to get into vectors, but we have to recall some one-dimensional motion properties, things that we've learned before and used quite a bit and should know pretty well, because that lays a foundation for everything that we're going to do in more than one dimension, which is when we're going to be using vectors. So let's recall some stuff. So if I said S of t is the position function of an object, then, how do you find the velocity function? Well, of course, we know if we take the derivative of the position function, we get the velocity function. If we take the second derivative of the position function, which is the first derivative of the velocity function, we get the acceleration function. We don't need to worry about jerk for this, okay? Basic stuff that we've been dealing with for almost 2 years now. We also know, that I want that speed is the magnitude of the velocity vector. Okay, so those are some things that we need to know. There's a few more things. We learned how to calculate displacement in a couple different ways. So if I want the displacement of an object on the interval from A to B, one way we did that was to just take the difference between S of B and and S of A, take their difference. In other words, find the position where it ends and subtract from it the position where it was at the beginning. We learned later that we could do this with the definite integral, that the definite integral from A to B of the velocity function is the same thing. That's just a consequence of the fundamental theorem of calculus. Then we learned a little bit more about motion and related the integral to total distance. And so we saw that the total distance, now I gave you a complicated way of doing this with the position function where we were looking at, every place the object changes direction, we would stop and break the interval up around those points, take displacements on each of those intervals, and then take magnitudes and then add them together. But we later learned that we can accomplish that much more quickly with the definite integral of the absolute value of the velocity function. And then we talked about when an object is speeding up and slowing down. We said that an object is speeding up if the velocity and acceleration have the same sign, SIGN, and then slowing down when the velocity and acceleration have opposite signs. Now, again, this is all the foundational stuff that we are going to build on. One last thing I want to remind you of is if we're talking about the XY plane, so let me get just a small little XY plane here, and I have some vertical distance between some point here and some point here. The way I would calculate that distance is top minus bottom. And if I had some horizontal distance, then we would take right minus left. It's always the greater minus the lesser. Why am I putting minus? Because I'm saying the word minus, trying to write something else, and my brain doesn't work too well that way. So these are some of the basic things in one dimension that we were working on to find properties of an object as it's moving. Now, one-dimensional motion is still motion described by vectors, but it's just not very interesting because it only has really one component, meaning it moves side to side or up and down, but it doesn't move at an angle. If I have an object that moves at an angle, and we're going to consider the straight line motion, say starting here and ending here, well, if I want to know how far away it is from where it started, I can't do a top minus bottom or a right minus left by itself. I would need the length of this thing. And to find this length, you guys remember, I'm sure, from geometry or an earlier math class, you'd run the Pythagorean theorem. We'd find out how long this length is and how long this length is. And then we would, let's call this x1, y1, and x2, y2. And then we would do, like I said, find those lengths and do the Pythagorean theorem. So this one here would be x2 minus x1, and then this one here would be y2 minus y1. And so the length of this, which I'm going to call A, and this is now a vector, so I'm going to put a little vector bar on here. The magnitude of A is going to be the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 quantity squared. And this is the key. The Pythagorean theorem, this relationship that I just described, is the key from going from one dimension to a higher dimension, to 2 dimensions is really what we need to do. And so if you can take everything that I just described up top and then know that to get magnitudes in 2 dimensions, we're going to need the Pythagorean theorem, you can do almost everything that I need you to do. All right, now let's get into 2 dimensions. Oh, it looks terrible. 2 dimensions. Okay, just put it like this. So a vector is essentially just a set of parametric equations. So if you went through the parametric equation stuff, then you have a foundation for vectors, okay? And so a position function and we put a little arrow for a vector. The position vector, I should say, for an object in 2 dimensions is sometimes written with parentheses, and it's sometimes written with angled brackets, sometimes written with other notation depending on the author of the textbook. I'm going to use the angled brackets here, but if it's given with parentheses, that's fine. And I think on the AP exam they might do that, but I didn't go look at it right now, so it's not fresh in my mind. So the position vector is just a set of parametric equations. So it tells me, it gives me a description of the x coordinate as a function of time, it gives me a description of the y coordinate as a function of time. Okay, so this is really just, some s of t. So how do I get the velocity function? Or the velocity vector, excuse me. Well, the velocity vector is just the derivative of the position vector. We should put the plus t's in here, which means I'm just going to take the derivative of each component individually. Nothing special here. Just like this. And how do I get the acceleration? Same thing. Sorry about this long bit of notation here, but this is just going to be this. And these are vectors. Okay. So let's go back up to the first example for a moment. The x coordinate here, x of t, describes the location of the object as it moves side to side. The y coordinate describes the location of the object as it moves up and down. But we're just combining these 2 motions into one set of parametric equations. When you throw a ball across the room, it's not moving in 1 dimension. It's moving in 2 dimensions, maybe even 3, depending on how you're referencing it. It's moving horizontally if you throw it across the room, and then it moves up and then down. So it's moving in the horizontal plane and it's moving in a vertical plane. And so, well, if you're looking at it from transverse moving, you'd see it like going across the vertical plane, moving horizontally, moving vertically. I don't like the way I describe that, but I think you get my point, okay? Throwing a ball across the room from a perspective of watching somebody do that, it's going to look something like this. So it moves both up and down, and it moves side to side. That's a better way of saying it. Okay, the side-to-side motion is determined by the x coordinate. The up and down is determined by the y coordinate, x of t and y of t. So if I want to know its horizontal velocity at some point, that's just x prime of t. If I want to know its vertical velocity at some point, that's y prime of t. And then similarly for the acceleration. Okay, just some real basic stuff. Okay, what did we remind ourselves about speed up above? We said speed is the absolute value of the velocity function. Well, speed is still the absolute value in 2 dimensions of now the velocity vector. What does that mean? Well, I told you a moment ago that the magnitude of a vector is just achieved or found by the Pythagorean theorem, okay? So how do I find the magnitude of the velocity function? Well, it's the square root of the square of the x-coordinate, x prime of t, quantity squared, plus y prime of t, quantity squared, okay? I just figure out that magnitude by the Pythagorean theorem. Sometimes I'll even ask them questions, what is the magnitude of the acceleration? Magnitude of the acceleration. There's no special word for it, like speed. So they give it as this whole phrase. What's that? Well, that's just this. And how do we find that? With the Pythagorean theorem. Just an application of what we already know how to do, just understanding that to get that magnitude. In one-dimensional motion, we don't need the y-coordinate. So the square and the square root cancel, leaving you with a positive result. So let me give you a quick example, a very simple example, okay? So let's suppose that the velocity of an object at 3 seconds is equal to -10. Okay, well, what's the speed? This is in one dimension. It's not a vector here. So what's the speed of the object at 3 seconds? All right, t equals 3. Well, it's the absolute value of -10, okay, which of course is just 10. Now, we could use the sledgehammer of the Pythagorean theorem like I just showed you and say, and imagine that since we're doing one-dimensional motion, let's say this is only in the x direction. So this would be -10 quantity squared, but there's nothing going on in the y direction, so that's 0 squared, and that still works out to be 10, just as we found before. But in one-dimensional motion, we just look at it as just pure absolute value, okay, because that's equivalent to it. And so we don't think about it on the level of it's an application of the Pythagorean theorem, okay. So now if I know that the velocity of some object moving in 2 dimensions at t equals 3 is given by the vector -10, 8, that's fine, doesn't really matter. And I want the speed, then how do I find that? That's just the magnitude of the velocity vector, which is found by the Pythagorean theorem, like this. And so what is that, 160, square root of 164? I don't care more about it than that, okay? So that's fairly straightforward. How do I find total distance? Now, let me give you something a little more precise. This is the speed, or rather the velocity at a specific moment. Let's suppose the velocity function was, as a function of t, was given by -10t, and let's go 3t squared just to make something up here. So then, if I wanted the velocity at 3 here, then of course that would be -30, 27 when I plug 3 in for t. If I wanted the speed at 3, then I would do the Pythagorean theorem. I'm not going to bore you with that right now. What if I wanted the total distance traveled on some interval? Let's say on the interval from 0 to 3. Well, total distance integral is the definite integral from 0 to 3 of the absolute value of the velocity function. Now the velocity function is in 2 dimensions. But how do I find magnitude? Oh, it's the Pythagorean theorem, okay? So what's v of t? Well, the x-coordinate is -10t. So it's the square root, and then we get this -10t quantity squared plus 3t squared, and we integrate that with respect to t, and that's how we would get our total distance. That should look familiar to you. That's at the tail end of the notes that I gave for gave for the parametric equation. Okay, this, I'm going to put this in a slightly different form over here. Okay, just so you can recognize it, I hope. Okay, this is the same thing as x prime of t quantity squared plus y prime of t quantity squared under the square root. And I'll be honest with you, I don't know the exact form I gave it in the notes, so I might have given it this way instead. So I'm going to give it to you both ways to cover my bases. Actually, this should be a dt over here, not a dx. Excuse me. But both of these here should be recognizable as the arc length. So if I'm talking about some position function, some position vector, then that position vector is going to describe some path of some object as it moves in 2 dimensions. Let's say it starts here, moves along with this orientation, to use terminology from the parametric equations, and ends over here, okay? If I want to find the total distance traveled, I want to find the length of that curve, okay? What's the length of that? How do we find the length of that curve? Well, I gave that as the definite integral from a to b. If this is, let's just say a and b are my starting t values. A is my starting t value, b is my ending t value. And then I gave it to you as just dx over dt squared plus dy over dt squared under the square root. That's the arc length. Well, that's going to be the total distance traveled. Okay, that's the length of that arc. That's how we get our total distance. That's our total distance integral. It's the same thing. It's the stuff we already know, put in different language with one tool that you've been using since kindergarten, the Pythagorean theorem, to work out the details of this stuff. Now, I'm going to give a separate video with examples. I'm going to pull questions from different sources, and we'll go through a few things. I'll even show you probably show you an animation dealing with this. Actually, I might do that now. Let me pause and see about that. So what I'm showing for you here is the location of an object given by the vector that you see up here in the brackets. I'm using x's instead of t's just because of ease of the way I was setting it up. But the x coordinate is given by 5 times the sine of x, or sine of t. And then the y coordinate is given by 8 times cosine squared, okay, of t or x or whatever. And up here you can see the position function at different values of x or t. So at t equals 4.2, the x coordinate is negative, so you see it going off to the left, negative 4.357, but the y coordinate is nearly 2, so you can see it going up. And as time progresses, you see, maybe you can imagine the tip of the arrow is tracing out the path of the object. The object's actually not on the body of the arrow at all. The path of the object is along the tip of where the arrow is always pointing. So maybe you can imagine it. Let me show it to you. Okay. It's just an upside down parabola here. Okay. You can see all of this. You can see the object traveling along this path. Now the velocity vector, I'm going to put head to tail with the position function. This is typically how it's drawn. What do I mean by head to tail? If you don't know anything about vectors, that's okay. The tail is the starting point of the vector. The head is where it ends over here, okay? So this is the head of the red vector, and this is the tail of the blue vector. The blue vector is the velocity vector. This is the head of the velocity vector, the arrowhead. And so you have to imagine a new set of axes. We have the original set of axes where the position function is at the origin. Now I put the velocity function at the origin of a new set of vectors that, or a new set of axes that starts at the head of the position function. So as the object is traveling along this path right here, its velocity vector tells you its direction. Okay, its x coordinate is pointing negative, its y coordinate is pointing negative. Now you can see it at this moment here, it's going to start moving along the path in this direction. Its y coordinate, its x coordinate is positive, so it's going to start moving towards the right. Its y coordinate is positive, it's going to start moving up. Okay, starts moving like this. And you can see the length of the vector However long the vector is the speed. Okay, that's the magnitude of that vector. Okay, and that length represents how fast it's moving. So as it's coming near this end over here, you can see the length gets shorter because it's slowing down. You can see when it gets longer, it starts to speed up, and then it starts to slow down. You can see it change direction over there. I can do the same thing for the acceleration function. That's in green, and then it starts to look even more and more chaotic, I guess. No, not chaotic, just confusing perhaps. I'm going to turn off those two for a moment. I'm going to turn on the position components. So you can see the direction, the horizontal and vertical directions being pointed by the vertical and horizontal arrows when it's traveling to the, no, well, this is position. So at this moment right here, okay, it's to the left this amount, negative 3.15, and it's going up almost 5, 4.8, okay? So you're just breaking those down by component like that. Let's take that away and let's put the velocity components in there. And I actually want to move this a little bit so we can see all of it here. So the velocity components that we see, here's the velocity vector. Okay, see the velocity vector is heading up at an angle to the right. It's got a small little displacement to the left. It's got a bigger displacement up. Okay, to the left it's negative 2.3, up is 6.6, and you can see those values there. And then you can watch the vectors change direction as the object moves. I can add the acceleration, I can add its components on here, and then now it really becomes confusing perhaps watching it at that speed, all these different things going on at once. I'll talk more about, and I'll do some examples of this stuff. Oh, I got to talk about in the next video also speeding up and slowing down. It's a little bit different, and we'll probably come back to this diagram here, but I want to keep this video short, so I'll do that in the next video. Go study.